So the inorganic chemistry part, chapter 16, acids, alkalis, and titrations. Let's get you introduced with all of these words, since most of them are new. So starting off with pH and indicators. The pH scale is the scale which can tell us how acidic or how alkaline a solution is. pH scale works from 0 to 14, as you can see in front of yourself. They have already divided the scale into 5 small parts. And this is going to work great for you because that way you can divide the whole scale and easily understand the parts. The first part is strongly acidic, which they have pointed out as from all the way from 0 to 3. Then there is a weakly acidic part, which works all the way from 4 to 6. 7 exactly is neutral. Anything lower is still acidic. Anything higher is still alkaline. In the same way, the next 3 steps are weakly alkaline, which would be from 8 to 10, of course, and the strongly alkaline portion will lie from 11 all the way to 14. They've given some very common examples in there. Hydrochloric acid is strongly acidic, vinegar is weakly acidic, pure water or sodium chloride solution or sugar solution, the sugar we commonly eat every day, uh, is uh, purely neutral, and then ammonia solution is weakly alkaline, sodium hydroxide solution is strongly alkaline. So that's how we know. Uh, pH scale is often divided into these parts in a very colorful manner instead of what we just saw, the black and white. We can actually divide it into a colorful manner, which we're going to study next. Now we can classify substances in the same way. These are 5 categories that we can talk about: strongly acidic or alkaline, weakly acidic or alkaline, and neutral. Remember, when we are writing pH, we write the P small, and this P actually talk about the potency. Potency means the strength. And the big H is actually the symbol for hydrogen, which means the presence of hydrogen. It means the strength of hydrogen ions in a system. That's a very good way of understanding what the word stands for. And that's how we are also going to define acids later on. Now,
Mhm.
strongly acidic portions and all the portions that I've just gone through are also stated over here with the examples I've gone through already. So moving on to the extension work. These are actually only approximate ranges. The actual acidity or alkalinity, the actual pH really depends upon the concentration of solution. For example, 0.1 mole per decimeter solution of ethanoic acid actually has a pH of 2.88. Not from 4 to 6, it's actually less than 4. So we can understand the point that anything can be concentrated or diluted in terms of removing water or adding more water,
Mhm.
respectively. Moving on, measuring pH. Measuring pH is the real fun part we were just talking about, since you have already told me that your teacher brought a whole set of solutions and he brought the indicators or the papers for testing in the class, and that little demonstration gave you an idea how we measure pH. So pH is usually measured with the help of indicators. Universal indicator is one of the most common indicator. It actually is a mixture of indicators. We mix too many indicators to just make sure that how the color will gradually change over pH values. We can use them as solution or as paper. The most common form is full range universal indicator. The name of universal indicator is also full range indicator. Full range indicator because it can work all the way from 0 to 14. So that's why we say it's a full range indicator. So the same thing is given over here, but it isn't really accurate. We will talk about what we can do for more accuracy. Actually, there is a hint present right over here, and they're telling you that pH meter is going to be far more accurate than any kind of pH or indicator paper. Moving
S-
on,
Sir,
right? Go ahead.
what is indicator like paper is made out of?
Indicator paper is a simple paper in which the indicator chemical is coated. That chemical changes color quickly whenever it is introduced to a solution of different pHs. And that's how, with the change of color, you can easily observe and judge what the pH change was.
Mhm.
So
All right.
it still is a simple paper coated with a chemical. And that chemical is commonly known as indicator. We're going to discuss a few indicators. We're right on the same point. So the chemical I was just talking about to you are actually acid alkali indicators. So we have quoted a good set of certain indicators over here, and we have also quoted the colors they are going to change. Now, these indicators are actually different chemicals. Some of them derived naturally, some of them made synthetically. These are the indicators which are also present natural. We will also come up with that example, maybe probably on the next page. If not, I'll explain the example myself. So indicators really are the chemicals that change or give different colors in different solutions. If we're talking about acid, means we're talking about anywhere from 0 to 6 range, or is acid, we're talking about anywhere from 8 to 14 is alkali range. And if I may add, and I insist that you should add this, then this is 7, neutral. So in case of litmus solution, if I be exact, if I call it litmus solution, purple or violet, it's neutral in it's sorry, purple or violet in neutral solutions. It's red in acidic. It's blue in alkaline solutions. Methyl orange, on the other hand, is red in acidic, yellow in alkaline, and orange in neutral solutions. Phenolphthalein is, or phenolphthalein, both pronunciations are fine, is actually colorless in both acidic and neutral solutions, but it is pink or light pink or pale pink, what we can call in alkaline media. Universal indicator, on the other hand, tries to imitate rainbow. It is also considered as a rainbow indicator, apart from the name universal indicator or full range indicator. We can also call it a rainbow indicator. Just like a rainbow, it works red in acidic, blue in alkaline, and green in neutral solution. You're going to see how it imitates that. Okay, let me actually check if we really have a diagram related to that one. There are diagrams in the book. We'll go through that. If not, well, it seems we don't have really that kind of diagram over here. And it's a
Mhm.
small chapter. So probably that's the diagram on the next chapter. Well, getting back to it, let me clarify that indicators are commonly present in flowers. You might have noticed that a kind of flower may come in many colors. For example, tulips are not just red, they show different colors. Roses are not just red. You can find roses in many different colors in their shape. Chrysanthemums are pretty common, or hydrangea is common. These are the plants that can show different colors based upon different kind of soils they are in. If they are in acidic soil, they show us a different colored flower. If they are in alkaline soil, they show us a different colored flower. And finally, the third color is showed when they're neutral. So we came up with the idea that if flowers can show different colors under different pH ranges, so can we in case of chemicals, and we call them indicators. All right.
Yeah.
Now, starting off with litmus, I intentionally wrote solution because I was giving a neutral color, which was purple or violet in this case. So since I was talking about a neutral color, it is specifically solution, but the key point over here gives you the idea that it can be used as a solution or it can be used as a paper. When it is used as a paper, it clarifies that it is only present in red and blue forms. The red turns to blue in alkaline solution, the blue turns to red in acidic solution. Universal indicator is green in neutral solutions. They have already clarified it, but since I wrote the whole table, it's not just about one or two indicators. You know the neutral color for every single indicator on this table. Moving on. So defining pHs, defining pH ranges, the whole scale, and talking about different kinds of indicators. Now it's the right time to introduce you to acids or alkalis. Starting off with acids. Some common acids that you probably be already familiar with, the names of which you might have already used in the book, is hydrochloric acid, HCl, nitric acid, HNO3, sulfuric acid, H2SO4. maybe ethanoic acid. We have been calling it vinegar all along, since ethanoic acid, vinegar is greatly ethanoic acid, or a solution of ethanoic acid in water, be it more or less, that really depends upon the concentration, that is CH3COOH, and finally phosphoric acid, which is H3PO4. Now you'd notice that if each formula has specifically hydrogen atoms in it. And those hydrogen atoms have been written in red instead of just these three. We'll understand this reason in organic chemistry. Let's keep it for now. You get the point once we'll get to organic chemistry. For now, we are going to give you a hint, but in this paragraph. Moving on, all the acids contain hydrogen, and when acid reacts, the hydrogen shown in red is replaced by something else. All acids have replaceable hydrogen. For example, when hydrochloric acid reacts with sodium hydroxide, this hydrogen is replaced by the metal sodium, and that's how we get sodium chloride salt out of this reaction. So the H of HCl has been replaced by an Na, sodium atom. Note, in a molecule, not all of the hydrogen atoms are replaceable. Sometimes the hydrogen atoms are not replaceable, like the ones in ethanoic acid. So if we have written them in black, but the hydrogen that is replaceable has been written in red. Usually, what you're going to find in the organic chemistry portion is that the ones joining carbon are not the replaceable ones, and the ones attached to oxygen are the replaceable ones. We'll discuss this in carboxylic acid, which is chapter number 27, one of the last chapters of the book, right? So moving on, when an acid is dissolved in water, they dissociate, they break apart, and they form hydrogen ions, which is a characteristic almost for every acid we have encountered in the table before. Notice, be it hydrochloric acid or nitric acid or sulfuric acid, whatever negative ion they give you can be different, but the positive ion they're going to give after they dissociate in water is always hydrogen ion. So when we measure pH, we are actually measuring the concentration of these hydrogen ions in solution. So the P was potency and H was actually a hint towards these H positive ions. So it's the strength or it's the amount of those H positive ions in a solution that we have been calling pH all along. So as soon as we describe this, it's really easy to define acids. And the most simple, straightforward definition would be acid is a substance that acts as a source of hydrogen ions in solution. At next level, you will discover that pH is defined mathematically with a mathematical system log of base 10, which we will definitely go for at advanced level. So you'll understand the pH scale more and in a much deeper context. Next up is bases. So base is any substance that can neutralize acid by combining with the hydrogen ions in them. We're referring to base at this level. We usually mean a metal oxide or a metal hydroxide or maybe ammonia or a solution in water. So you would now see that we just talked about bases, and when then we jump to alkalis. Let me tell you, alkalis are themselves as a subcategory of bases. How? Let's define them. Some bases dissolve in water. They form solutions that contain hydroxide ions. We call them alkalis. So if any base is soluble in water and this solution is going to give you hydroxide ions, we're going to call it an alkali. That's how the bases are categorized. Some bases are soluble, some are not soluble. If the base is soluble in water, you're going to call it alkali. If the base is not soluble in water, you're still going to call it a base. I hope that clarifies the difference between the bases and alkalis. So alkalis are a source of hydroxide OH negative ions in solution. Example of alkalis include sodium hydroxide, potassium hydroxide, all group 1 hydroxides. There are even some group 2 hydroxides in the list. So when these hydroxides are dissolved in water, they also break apart like acid. They give us positive ions, and the good part about all of them is that they are going to give the negative hydroxide ion as soon as they dissolve in water. We also called ammonia a base or an alkali. Why? Because ammonia gas reacts with water, not just dissolves in water, reacts with water to produce the ammonium ions. And apart from that, are traditional negative ions, the hydroxide ions, which is actually common for all alkalis. Now, as we say that the acids have a pH less than 7, they haven't mentioned it over here, but we have said it on the very first page. You're going to notice that we write all alkalis have a pH greater than 7. Apart from alkalis, there are some alkaline solutions. There are soluble metal carbonates. They can also react with water and they can give us some alkaline solutions, or they can directly produce alkalis upon reaction with water, like sodium carbonate is, which is commonly known as washing soda. So the detergents that we commonly use produce a slight amount of alkalis in the system. Ammonia solution is sometimes also known as ammonium hydroxide. That's a very important point. I insist my students that sometimes we leave out the captions under the pictures in our chapters, but this specific one, please don't leave it. Mark it so that you can memorize this. And remember, the ammonia solution, which we have been calling NH aqueous, can be written as NH4OH, and this formula is pretty obvious from this line. Notice ammonia, when react with water, forms the positive and the negative ion. If I combine these two ions in a single formula, you'll get the formula NH4OH. So ammonia solution is ammonium hydroxide, which is actually a really good cleaning product. Some universal indicator solution has been added to it, and you can see the color blue, which uh, gives us the idea that it's a weak alkali.
Mhm.
Moving on, there are not many soluble carbonates, but sodium and potassium carbonate have both alkalis with the pH greater than 7. This is because they can produce OH negative ions in the solution. Only some of the carbonate ion reacts with water. The solution is only weakly alkaline, and that's the equation that we commonly use for the carbonate ions in water. This equation, though it is written as a part of extension work, has been a part of your past paper exams. You need to mark this one as important as well. So that's how the carbonate ions CO3 negative 2 react with water and they produce OH negative ions, which makes the whole system slightly or weakly alkaline. And they also produce the hydrogen carbonate ion, which means this is now the right time to discuss the reactions of acids or alkalis or bases among one another. So acids tend to react with both bases and alkalis, and it's pretty much the same thing. We're just talking about the differences water solubility between both. So acids, when they react with either bases or with alkalis. We call that a neutralization reaction. Neutralization because acid can neutralize the alkali can neutralize the acidic effect. If I say that they both neutralize one another in this reaction, that would be a very accurate statement. Reacting acids with bases, how does we go with it? Remember, we told you that bases are the metal oxides, which are not soluble in water. So copper 2 oxide or magnesium oxide are very good examples. So take some copper oxide, react it with hot dilute sulfuric acid in a neutralization reaction. What's going to happen is that the oxide will react with the acid and it would give you salt and water. This is a very good way to memorize this equation. So when a base reacts with an acid, it gives you salt and water. If you keep this stuff in mind, you would know that every time when an acid and a base react, it gives salt and water. How do we go about this reaction? Take a look at this part. This is the acidic part, H. This is the oxide part, O. This is forming H2O. And we combine the rest, copper, with the sulfate ions to form copper sulfate. This is how easy these reactions are. I hope this makes sense. If you are going to work your way around these reactions in the same way, taking hydrogen out of the acid or oxygen out of the base and forming water with it, combining the rest, forming salt with it, every time you're going to land at a correct equation.
Mm-hmm.
So
All right.
copper oxide is an ionic compound. It consists of oxide ions and the acid has 8 positive ions. They combine to form water. They have cleared one part of it, while I've cleared the rest of it too, so that the rest combines to form salt. And the further clarification is given over here. So this clarification talks about acids reacting with alkalis. This time, remember, we're talking about an alkali. This means that this is water soluble, which means we can dissolve it in water and form an aqueous solution. Hence, our very common example, sodium hydroxide, which is a great alkali because it easily dissolves in water, since the state symbol aqueous solution. The acid is also converted into an aqueous solution. Both of them reacted. And again, alkali plus acid give you salt. And this time, clearly, we are landing at a very easy salt, the salt that we eat every day, and water. So good part, be it an alkali or it in base, whenever they react with acid, they produce salt and water. And pretty much that's the easy stuff. So take the H out of acid and the OH out of alkali. That's how it's going to form H2O. So H plus OH is going to give you H2O. If I be exact, that is H positive, that is OH negative. That's how water forms. Combine the rest, you have sodium and chlorine, or if I be exact, sodium ions or chloride ions, which are written here in this green and red color, you'll get your salt. But if I write this as ionic equation, I do understand that the salt is spectatorine. Neutralization reaction is all about forming the neutral product water, which is formed by H positive coming out of acid, the characteristic of acid, and OH negative coming out of alkali, the characteristic of alkali. So this is the ionic equation we end up with for every neutralization reaction. And that's a great way to talk about every neutralization reaction of acid and alkali. You're going to end up with having H positive plus OH negative, giving you water, which is great.
Mhm.
Now, this ionic equation is going to work as a great tip for you. How? For any of the alkalis, let's say the alkali is KOH, for any of the acids, let's say the acid is HNO3. I've changed the acid, I've changed the alkali. Now do the same thing. H and OH are going to combine to form water, and K and NO3 are going to combine to form salt, KNO3. There you go. You have your salt, you have your water. You end up with the same thing. And let me tell you, the spectator ions are the salt ions. These are salt ions and they are spectator. Why? They are a collateral product in this neutralization reaction. Since the reaction was solely all about the H positive ions coming out of acid, OH negative ions coming out of alkali, forming the neutral product water, hence the name neutralization reaction. All right. So I
Mhm.
hope this all makes sense. Does it?
Yeah, sort of.
Good. Good. So we are only left with the titration part. So recapping acid, it's going to be pretty simple. Acids are going to contain hydrogen atoms, and whenever dissolved in water, those hydrogen atoms will be coming out as hydrogen ions. And that's the characteristic of an acid. Not all the hydrogen atoms come out as hydrogen ions, so only a few of them are replaceable for some specific acids. So what we do is that we define acid by the very source of hydrogen ions in solution. That's the way we define it. So all acids can react and they can displace their hydrogen atoms. On the other hand, bases is anything that can neutralize acid, and they tend to combine with the hydrogen ions in them. They don't worry about what's the negative ion, they tend to only combine with the hydrogen ion. A base can be a metal oxide, a metal hydroxide. Metal oxide means MO, metal and oxygen. Metal hydroxide means MOH, metal and an entire hydroxide ion, which is OH, or it can simply be ammonia or ammonia's gas solution in water. So as soon as we get to bases, actually we don't go for them anymore than going for alkalis, and these are the specific subcategory of bases which is soluble in water. So if the base is soluble in water, we're going to call it an alkali. And the good part is that alkali is going to give you hydroxide ion. So just like acids were source of H positive ion, alkalis are a source of OH negative ion. Now, is going to make sense later on that this H positive from alkali and this OH negative from, uh, my bad, this H positive from acid and OH negative from alkali is then going to later on combine to give us water. So water is the neutral product having the same amount of H positive ions from an acid or OH negative ions from an alkali. Hence, we call this reaction a neutralization reaction. Hence, we have been using the word neutralize for acids and alkalis for these reactions in specific. Getting back to alkali, any group 1 hydroxide acts like an alkali. Why? Because as soon as it is dissolved in water, it gives you OH negative ion. Good part, alkalis have a pH greater than 7. Ammonia is also an alkali because it reacts with water, not dissolves in water, reacts with water to give us OH negative ion. Moving on, there are some other alkaline solutions. For example, carbonates can also react with water to give you OH negative ions or alkalis, but not all carbonates can do that. When you react with a base with an alkali or acid base with acid or alkali with acid, you call it a neutralization reaction. A neutralization reaction is completely like a reaction in which base or alkali may react with acid, and there are two certain products out of this, and that is salt and that is water. So the same thing happens over here. Take a look. We reacted a base with acid, we got a salt, and we got water. How are you going to do it? Take H out of acid, take O out of base, form water with it, combine the rest, positive ion of the base and the negative ion of the acid, and you get your salt.
Mhm.
On the other hand, if I talk about the reaction of acid with an alkali, the same thing happens. You take H out of the acid, you take OH out of the alkali, you form water out of it, which is neutralization reaction, which is the actually neutralization reaction. The rest is spectators ions, and those are the ions which form our salt, the positive part of the alkali and the negative part of the acid. So the ionic equation for any neutralization reaction ends up in H positive plus OH negative giving you water. And that was all about for today.
Mhm.
Are we good?
Mhm.